Images and audio do not enter a language model as raw pixels or waveforms. Hi, I'm Mehrdad. In this lesson, we'll see how multimodal models turn media into numerical representations and use them alongside text. We'll begin with a practical question. Why can adding one image make the input much larger? The same task can require different sequence lengths and different amounts of computation before generation. A text-only request may occupy only a few token positions. In a unified sequence vision model, attaching an image adds visual embeddings to the model's context sequence. Depending on resolution, how the image is divided into fixed-size blocks, tiling, and compression, one image may add hundreds or thousands of positions. The added positions increase sequence length and pre-generation computation. Cross-attention architectures retain visual features outside the text sequence, so we should not assume that every multimodal model uses a unified token sequence. The precise questions are these. How does the system represent the media? How does the system integrate media with text? And what computation does the selected architecture add? If this series is helpful, like the video and subscribe. First, ask how raw media becomes embeddings the language model can consume. A common vision system uses a modality encoder and an adapter. The vision encoder converts fixed-size image blocks into visual feature vectors. An adapter, projector, resampler, or merger maps those vectors to the language model's embedding width. A merger or resampler may also reduce the number of visual positions. The language model consumes the mapped vectors as visual token positions. Audio encoders produce sound feature vectors, and audio adapters map them to audio token positions. Some architectures skip a dedicated modality encoder and project fixed-size image blocks or audio chunks through lightweight embedding layers. This representation path explains how media becomes token positions, not how those positions interact with text. Next, ask how visual or audio representations interact with text representations inside the model. One architecture keeps modality features in a separate sequence. Cross-attention uses language hidden states as queries and modality features as keys and values. Another architecture inserts visual or audio embeddings beside text embeddings in one sequence. Shared self-attention then processes all token positions together. Papers often call these mechanisms late fusion and early fusion, but the labels have inconsistent definitions. The exact mechanisms are separate modality features with cross-attention, or a unified token sequence with self-attention. Either integration mechanism can still use a dedicated vision encoder. Integration is therefore separate from representation. We now have three separate design questions. First, what representation path converts pixels or sound into embeddings? Second, does the model integrate modalities through cross-attention or a unified token sequence? Third, which components were trained together? A system may align separately pre-trained modules or jointly optimize its modality representation layers and language model layers. The phrase natively multimodal usually describes joint multimodal training or a product capability claim. Natively multimodal does not identify a specific integration mechanism, prove the absence of a modality encoder, or imply image generation. Keeping the three questions separate prevents category errors. Apply the three questions to real systems. Llama 4 uses a vision encoder, then places visual embeddings into a unified model sequence. Llama 4 is therefore not encoder-free. Gemma 412b unified projects fixed-size image blocks and audio chunks without dedicated encoder towers. The encoder-free claim applies to the unified model, not every Gemma 4 model. GPT-4o is described as trained end-to-end across text, vision, and audio. OpenAI does not disclose its detailed representation and integration mechanisms. The three cases are not a ranking. For each model, record the disclosed representation, integration, and training facts. Mark every undisclosed field as unknown. QN3VL gives us an open example we can inspect. Its representation path starts with a vision transformer that builds features from fixed-size image blocks. A multi-layer perceptron merger compresses and maps those visual features into embeddings for the language model. The visual embeddings occupy token positions in the model sequence. The system also tracks position across video time, image height, and image width. Interleaved multimodal rotary position encoding modifies the queries and keys. Interleaving rotary frequencies across temporal, vertical, and horizontal axes avoids treating an image like a single line of text. Deep Stack sends features from several vision layers into early language model layers without adding token positions. For video, sampled frames and text timestamps preserve each frame's location on the timeline. Audio can enter through two main paths. In the first path, automatic speech recognition turns speech into text before the language model receives it. The downstream language model processes ordinary text tokens, but transcription may discard prosody, timing, emphasis, and non-speech sounds. A recognition error also reaches the reasoning stage as incorrect text. In the second path, an audio encoder converts sound features into audio embeddings. A unified sequence model places audio embeddings in token positions, while a cross-attention model keeps audio features in a separate sequence. Audio embeddings can preserve prosody, timing, emphasis, and non-speech sounds, but audio encoding and cross-modal integration add computation. The application must choose between an ordinary text token interface and access to those acoustic properties. Now return to the visual token count from the opening. A short text prompt may use only dozens of tokens, while one detailed image can add hundreds or thousands of visual positions. Larger images contain more fixed-size blocks. Dividing an image into smaller blocks increases the count again. Some systems divide a large image into several tiles, which also increases the position count. A spatial merger can reduce the count by combining neighboring visual features. An adaptive compression policy can assign more positions to detailed areas and fewer positions elsewhere. Some application programming interfaces calculate build input tokens from image resolution and tile count, although each model family defines its own policy. Resolution, tiling, merger compression, and adaptive compression therefore set the visual token budget. The model must process every visual position before producing its first output token. Video 9 will show how visual positions increase pre-fill work and affect the key value cache used during decode. Each modality introduces specific failure modes. Optical character recognition can misread small text, tables, and complex page layouts. Visual grounding can attach a claim to the wrong object or chart region. A model can also invent an object or chart value that is not present. A speech-to-text path can discard prosody or pass an incorrect transcription into reasoning. Images and documents can contain hidden instructions that trigger prompt injection. We'll examine multimodal prompt injection in video 24. Measure computational requirements and output reliability separately. Token positions, pre-fill latency, and memory use describe computational requirements. Recognition accuracy, grounding accuracy, transcription accuracy, and task success describe reliability. A polished demo does not establish token count, latency, memory use, or task accuracy. Keep 3 ideas from this lesson. Representation, integration, and training are separate decisions. Media embeddings can add token positions, so test both computational cost and modality-specific failures. I'm Mehrdad. If this lesson helped, subscribe to Multi-Agent Academy and find me on LinkedIn. Next is video 9, Pre-fill versus Decode.